Hello, this is Mr. McGovern. This is the third video in the Level 3 series on modern physics, and we're going to look at the results of the photoelectric effect and why they're surprising. So I introduced this experiment in the last video. If you haven't watched that, watch it now. We're going to talk about what current and voltage mean within this experiment, and then three results, and then trying to explain those results using a wave model of light. So the first thing is, here's the experiment going again, and you can see this light being pushed onto the metal and electrons escape from that. Electrons hit the other side. We can change the intensity, and what we can see is when we change that intensity is the current changes. The amount of electrons coming out of the metal change, and the current changes as well. So we increase the intensity, more electrons come out, and we have more current in the circuit. So current is really a measure of how many electrons are being released from this piece of metal. So when you think current, think number of electrons. The other thing is here we have a battery, right? If we give that a positive voltage, what that does is the electrons are attracted to the side they're already going to, and they accelerate. Okay? They go faster and faster and faster, but there's nothing we can really measure there. The current doesn't change. However, if we go negative, the right side becomes negative, and you see that the electrons are slowed, and we get to a point where we can slow all the electrons, and the current becomes zero. So that's something we can measure. The voltage decelerates the electrons. We can measure what voltage that is, and really what that means is that voltage is a measure of the energy of the most energetic electrons. So current is how many electrons are being ejected, and voltage is effectively what it takes to stop the electrons, effectively, rob them of their kinetic energy. So therefore voltage is a measure of the energy of the electrons. So observation 1. What we do is we change the intensity, so the brightness, and we see that more electrons come out. The current increases. We keep changing that intensity, keep making it brighter and brighter and brighter, and we get more and more current, and we get a nice linear graph there. More current, more intensity, which means more electrons. So more light intensity was more current. That kind of makes sense, right? Observation 2. Here what we're going to do is we're going to figure out what voltage we need to stop all the electrons. So I make it negative, and you see I've got zero current here, and you can see that graph there, that the current goes down to zero at negative 1.2 volts. Around negative 1 volt, right? But my intensity is at 100%. So what I'm going to do is I'm going to change the intensity so it's not as bright, not as many electrons come out, and see what happens. So we'll just bring the voltage back to 0, and we can see that even if it's positive, it doesn't really change the current. The same amount of electrons are ejected. So let's now change this intensity. So we get less electrons ejected, but what do I need to stop them? And so you can see I still need about negative 1.2 volts to stop them. So it didn't matter how bright the light was, bright light or half bright light, it still required the same amount of energy to stop those electrons, even though there was less of them. So that's the second observation. The more light intensity does not change the energy of the electrons. Okay, so here's a graph of two intensities. Lower intensity, we get less current because there's less electrons coming out. But what voltage does it take to stop them? The same as when it was really bright. And the third observation is now we've got a whole bunch of electrons coming out, and we know we need some sort of voltage to stop those electrons. What happens if we change the color? So the color is wavelength or frequency of the light. So let's make it more higher frequency, and you see these electrons are flying out. They're coming out with much, much higher energy, so I need a bigger voltage to stop them. So at a high frequency, which is low wavelength, UV light, I need a really big voltage to stop these really, really fast electrons from coming out. If I change that frequency, you see that the electrons being ejected are coming out slower. So I'm probably going to need less and less voltage. They're coming out slower again as I get a lower frequency, slower, until it gets to the point where no electrons are ejected at all. So I don't need any voltage to stop them because they're just not being ejected. So I can graph that, what energy they come out with versus the frequency, and remember the energy is just from the voltage. So if I get into the reds, which are low wavelength, high wavelength, low frequency, no electrons, and then slowly become higher and higher frequency, and we slowly start to get some energy in those electrons. High frequency, the energy increases again and again and again, and we get this graph. So there's a point in this graph where we get nothing. This frequency here is called the threshold frequency, and over that frequency we start ejecting electrons. So and then as we go higher and higher frequency, which is more and more towards the UV side, towards the left side of that scale, the electrons, you could see them coming out faster and faster and faster. So increasing the frequency increases the energy of the electron. So let's try and explain these three observations, thinking about light as a wave. So what I think about, the metaphor I use is, instead of light hitting metal, I just think about waves hitting a beach. And on the beach there's lots of sand, they're the electrons. So what does it take to dislodge that sand in my wave model? So more light intensity meant more electrons. So intensity in waves at the beach is the height of the waves. Bigger waves make sense that I'd push away more sand, right? So bigger waves knocks more electrons off. That makes sense. That's explainable. So we can give that a tick. What about the next one? The more light intensity does not change the energy of the electrons. So think about a wave hitting a beach, and bigger waves, surely that would hit the sand away further, give the sand more energy. So I feel like that's not really explaining the fact that what we actually see in the photoelectric effect is that if we change the intensity, it doesn't change the energy of the electrons. So I would think that bigger waves would give the electrons more energy if I'm thinking about waves. So that's not really explainable using our wave model. The last one is increasing the frequency, so how many waves are hitting the beach every second. I don't think that thinking about waves would actually change the energy of the electrons, or if I'm thinking about my wave hitting the beach model, just getting more waves hitting the beach doesn't really change how much energy bits of sand are getting. So again, there's two observations here that are not really explainable using a wave model of light. And in the next video, which is the last one, we'll introduce a new model of light which happens to explain all of these three observations.